Hi there. This video is going to be about the numerical codes that we use to, or a couple of them that we use to calculate the scattering phase shifts and the cross sections. And in these codes, right now they're just for spherical interaction potentials. And also they are going to be they're going to have basically an analytic form, which means I don't need to do a long computation to calculate the potential and then read it in or import it into the code. But let me go ahead and show you the first one. Here. So this one is called NUM-SPH.4, and it uses the Numerov method. And right now it has a test potential that it's going to calculate the phase shifts for. But all of these codes generally have the same structure. So let me just go ahead and kind of go through it. So first of all, I start making everything double precision up here. And then I define a couple parameters. N is the number of steps. So basically these integration codes will start near r equals 0 and integrate outwards progressively. And this will make 1,500 steps. I'll define later the step size, or the size the size of the step I take in r, going out from the origin. L max is the maximum number of angular momentum, number of L's. K max is going to be related to the maximum velocity steps, right? I'm going to change the velocity or the energy of the incoming electron with this number of steps, 50. Now I dimension our mesh here, RMSH, is the kind of the grid. So let's say I start at r equals 0.01 and I step out by 0.01, right? It's going to be that grid that is defined by stepping out every 0.01 points. Now UL, it has a couple of indices here, but this first one is just for spherical codes. We don't need it really, so I set it equal to 1. But it's going to be defined on the R mesh, right? So it's a function of R at each of the points. So it has the same dimension, 1,500 points. Phase here, 0 L max, says that these are my phase shifts, and I start at L equals 0 and go up to L equals 4, right, up to the maximum value of L. Now I define a couple external functions, AK and spherical and SVES. This is the calculation of spherical Bessel functions that we need for the asymptotic solutions. AK is the momentum, the K, the square root of 2ME that we get in the asymptotic region. So it's the asymptotic momentum. I'm also going to convert that to energy if I need to, EE. And I have a common block here. What this does is anywhere you put it in your subroutines, it will share whatever is in these variables with the other subroutines. Now pi, this is just the definition of the constant pi. Each step down here is the step size of the mesh. So in this particular program, I'm just stepping out in steps of 0.01. My initial step in R is 0.01, so that's the initial point of the of the mesh. My initial velocity step is 0.02, right? So I'm starting with a velocity of 0.02, and I'm stepping out in that same step size of 0.02. So if I go 50 step sizes, it should get me out to, let's see, I think 1, a velocity of 1. Let's see. Actually, sorry, not quite a velocity of 1. But you can change all of these if you want to, change how far you integrate out in velocity or your step size. Sometimes you need to change your integration mesh to make it tighter. If the potential is big, for example, to make it more numerically accurate. So now we start our loop over the velocity, right, or energy. V equals VI. Do 2 says to go and loop all the way down to loop 2, right? From 1, and I'm running over index I from 1 to my maximum K, my maximum energy. Now my energy is just the kinetic energy, 1/2 mv squared, but for electrons, m is equal to 1 in atomic units. I have to change this to 2 if I'm dealing with positronium, for example. But positrons and electrons have a atomic mass units of 1. So this is just my kinetic energy in the asymptotic region. Now I'm going to loop over the angular momentum. LA here. Now I kind of, you can see I actually stopped the loop. I'm just choosing LA equal to 2. And LA is given by, or my AL2 here is my L times L plus 1. Now, you could change this if you want to actually loop, and what you could do is just set, L, take out the C, the comment marker, and just set this to set L equal to LA, or LA equal to L, and this way run the program and loop over the actual values of L. So again, sometimes when I run these programs, I make these changes. Maybe I want to just print out or look at the particular L equals 2 contribution to the partial wave, and so I'll comment something, comment out the loop, and it will just go through L equals 2. But you can experiment with putting the loop back in and seeing what happens, right? Is take out the comment here, and what you'll probably have to do is, again, I've got an L here, but I've defined everything in my integration stuff as LA, so you're going to have to put a line in here, for example, that says LA equals L or something like that. And in order to do that, I will let you do that if you want. But at this point, I'm looping now over all the L's. Now, I've got to do my integration steps, right, or my steps outward, starting with the first 2 initial values at r equals 0 and r equals 0.01. I have some initial values, or some boundary conditions, I guess you could say, and I'm going to integrate out using those. And the Numerov method does this. I'm not going to go in through the details here in this video of the Numerov method, but all of this code right here, this actually is my first Numerov step, so it will take it out 1 step. And then I do the remaining steps down here in this loop, do 10, right, to 10 continues. So this loop right here does the remaining Numerov steps. And you can see this UL, it actually will give the radial function down here. As I step out, it'll put it on the mesh. And I could, and I think there is later in the code, a place to print that out if you want to print that out and look at what your solution looks like. But for scattering calculations, we are going to now calculate our inverse logarithmic derivative, right? You can calculate the logarithmic derivative, but often people use the inverse of it, and it's called the R matrix in more sophisticated scattering problems. But I calculated it n-1, so 1 before the n step. And the reason for that is because I need to get R sum here. Now, R sum, in this case, is my Kr, right? It's my velocity or my momentum for an electron times the R at that point. And then the UP is the derivative of the wave function at n-1. So I just do that by taking the difference of the radial function surrounding that point divided by the difference in R, right? So it's just like delta U over delta R, basically. And then I get my inverse logarithmic derivative. I take the wave function or the radial function itself at that point, and then I divide by UP. So it turns out I didn't even need this R sum to get that. I don't think I may need it anywhere else. It might be left over from other calculations I was doing. So at this point, I have the logarithmic derivative. Now I need to call and get the outer asymptotic wave functions, right? The Riccati, Bessel, or Neumann functions that we talked about, and their derivatives. So all of this code here does that. AK0 is my asymptotic K value, right? It's the K in the equations we had. SL is my S or J related Riccati Bessel function. Here I'm just using the asymptotic forms, right, that we wrote AK0 times R mesh at n-1 minus L times pi over 2. In other codes, I might actually calculate those more sophisticatedly, but I should be out far enough after 1500 steps that I'm well into the asymptotic region. And then I get the derivatives. So you can see, right, those derivatives are pretty simple. Derivative of sine is just a cosine. But again, if I'm dealing with more sophisticated codes, I got to be careful of my derivatives. Then I do the matching, and this is where our K-matrix stuff comes in. I'll let you kind of puzzle out that, but that really is the formula for matching, right? The inverse logarithmic derivative equal to the asymptotic forms. And then I get my phase shift, which is my tangent of my AKL, or my arc tangent, my inverse tangent of that. And then I just print the velocity versus the phase shift. And so you could actually plot, maybe using NuPlot or some other plotting program, you could plot what those numbers are. But if you run the code, it will actually just spit out those numbers. And I can show that here in a second. Okay, this is just a comment that probably could be deleted, but the way I wrote this particular code, I now, at the very end of my velocities, I do my velocity step here. So I make another step in velocity, go back to where it says do to, where it does the loop over the velocity up here and repeats it for the next velocity step. Okay, so hopefully that main code is kind of understandable. This function AK is used in the Numerov method, so you can see it up here. So what it does whenever I use AK right here, it just calls this and calculates AK as a function of X, whatever variable is put in there, which is R2 in my case right here. So you might have to, if you really want to understand the Numerov method, we can talk about that later, or you can look online. But it's a method of integrating second order differential equations like this. Now, the other thing I want to point out, here VR is the actual potential. It's included in this external function AK. Right now it's my test potential. It's just minus 0.7 D0. Now the D0 here, I always put that on the numbers because it designates them as double precision, which means instead of 8 digits, it'll go out to 16. You may not need to really do that since everything's implicitly double precision up here, but it's just a habit of mine. But this is the only potential that I'm using in this code, okay? You could change the potential there, right? You could put whatever potential you want and try to calculate and see what the phase shifts are. So this code is a little bit incomplete. It's kind of a building block. I don't have the cross-section in there. If you wanted to add a cross-section calculation, that might be a good exercise. You might change to a square well type potential and see what you get. See if you can get resonances or Ramsauer-Townsend minimum in your calculations. But that's the Numerov method. And a lot of times I use a different method, which again, we'll have to study the details of later. But let me show you the code for that. And it has the same general structure. But in this code, I use an integral equation type of formulation of the Schrodinger equation. And we could talk about the details of that later, but again, this code is a little bit more extensive, but it's basically the same structure, right? I define our mesh, UL, my phase shifts, my cross sections now. Now my cross sections are going to depend on the energy. So I kind of store them in this array as a phase shift that depends on L and K, the momentum or the energy. And I get a total cross section, TXC, and my velocities. I have an external Voltra. That's going to be my integration subroutine. So it's going to be a subroutine that I call every time I make a step forward in integrating the Schrodinger equation. This time I'm actually going to call the spherical Bessel function subroutine that calculates these Riccati Bessel functions. And VR is an external potential function. So if it's external, I got an external function, I can just change that function without changing anything in the main code. Makes it a little easier just to make changes and recalculate. But other things are pretty similar. I've got my step size. AKN now is my velocity. I don't know why I didn't call it V here, but either way, I do set up V of I equal to AKN, and my energy again is 1/2 mv squared with m equal to 1 for the electron. I set my initial, or my total cross section to 0. I'm going to do a sum later over all of the different values of L, right? The different partial cross sections. So I set the initial to 0 here at each energy. And then I start my loop over the angular momentum. And I have what's called a kind of Volterra equation when you do this integral equation method. But all of my integration actually takes place in this subroutine Volterra. So I put in call Volterra, and what's input into Volterra is N. 1 is the number of coupled channels. So we only need 1 here. This is a spherical case. I can do each value of L by itself. When you have molecules, they're coupled, and you got to do a bunch of them connected to each other at one time. The 0.01 is my starting point, my starting R value. I'm plugging in each step, which I defined up here to be 0.01. Our mesh is output now by the subroutine. So this is one thing in Fortran, you can bring stuff in, but you can also just put stuff here that will be output, right? It'll be changed by the program. So this little next step of this code is just if you wanted to print the functions themselves, right? The solutions, I would just take out this comment and run the code, and you would get a printout of that. But I don't have that here. Or I'm not going to use that in this case, so I commented it out. You could even just take this whole block out, and you wouldn't change the program. So once again, once I get my ULs from the integration Volterra, I define my R matrix, my inverse logarithm derivative, do my matching. Now I'm going to call this external function spherical Bess, SBess, and return all of my spherical Bessel functions and define my, I call them GL and FL, my Riccati Bessel functions, and get all of the, the asymptotic forms, do my matching. But again, my phase shift is A tangent of AKL. I assign it to my phase array here so I can keep track of them, and then I do the loops all over again. But at the end of each partial wave, right before I return for the next L value, I add to my total cross section. And so I can actually, at the very end, now print out my velocity, my phase shift, and my total cross section. Okay, so that's the main code. Here's the subroutine Volterra. We can talk about how that works, but basically it just returns, the F and the T, the R and the UL of R. The G1, G2, and AK1, AK, they're just functions that are used by the Volterra subroutine. Now I get down to my VR, my potential function. And you can see there are several potentials in here. Right now, it's using a model. This actually, for VR right here, is a static potential for electron helium scattering. And this is a model exchange potential. And then I've got my polarization potential. So it's got a static, exchange, and polarization. So if you actually run this code right now, it should output cross sections that come close to experimental helium cross sections. It actually works pretty well to give the right results. Now, this is a model potential. We should probably try to do better than that, but it does give correct results. I also have my test potential that you could try running this for up here. And my square well potential, this will actually give, if you wanted to try these parameters, just uncomment all of this, comment this stuff down here, it'll use this as the potential. And I can give you the results for that, and you can see if you're getting the right results, but you should see resonances there. You might see a Ramsauer-Townsend minimum there as well. You use that square well potential, right? It basically has a certain depth and a certain range. So I think that's basically it. Spherical Bessel, these codes down here just are programs to calculate spherical Bessel functions, and that's it for the code. So I'm going to go ahead and I think as a last thing here, just let me show you. I don't have my command prompt up, so let me get that real quick. So when I do this, I'm going to change my directory to the directory I have these codes in. Let's see which. And so then if I want to run the ints, the integration int sph.4 code, I just WFL386 int sph.4, and it compiles it and creates an executable file. And then I could just hit int sph, whoops, and it should run through. Now it's going to take a little time because I didn't have it print out at each step. What I did was I assigned, those arrays, phase and TXC that have all the cross sections in them. So we might have to wait a little bit here for it to actually get through the full calculation and then print it out. Maybe I should have shortened it up here a little bit. And I don't remember exactly how many calculations were 41. It shouldn't take too long, I don't think. But one thing we want to be able to do is to be able to put this in a file, right, a data file. And in order to put it in a data file, I can just actually run int sph and use the caret key. And it's taken quite a while to get all the way through the calculation. I can use the caret key. So let me stop this. And I'll just run the other code since that takes a while. Let's go ahead and share that screen again. So I'm going to go back to my directory. I just wanted to show you one thing that I need here. So run now the Numerov code. But when I run it this time, see, it just prints it to the screen. So now what I want to do is print it to a file. And you can name it whatever you want. We'll say phase out .dat. And so then if I go to that code, to that particular file, it'll create that file in my directory. And I can open it up in Notepad or with any graphing or plotting program I want. So I think that's it for this video. If you do have questions, let me know, but try to play with those. The next step is that, I want to calculate potentials that are more sophisticated that I don't have an analytic formula for, and read them or import them into the program. So we can talk about that after you maybe play with these ones a little bit. And then we've hopefully got the basic tools that we need to continue forward.